Good day and welcome back for our final installment of changes of variables with double integrals. And I'd like to begin by making the same recommendation as I did in the previous video. That is to pause the video and give yourself some time to work through this example on your own. Something like maybe say 8 to 10 minutes would be reasonable. Even set a timer to make sure that you're spending the time to do so. Also, if you get stuck at a certain point, you can kind of watch just enough of the video to go on to those next few steps. And just to reiterate my comment from the previous video, this is an important part of the learning process, kind of working through this internally and maybe even struggling with the material a bit. Okay, so now assuming that you have done so, let's evaluate the double integral over this triangular region R of the function x minus 3y. Now note, in terms of this region of integration, we cannot directly handle this as a single type 1 or type 2 region as we have done previously, but note, you could divide it into parts. Maybe if you draw in the line x equals 1, you would have a type 1 region for the x values from 0 to 1, and then a second type 1 region for the x values from 1 to 2. That is to say, you could use two double integrals. And that would be a perfectly reasonable way to go about the problem, unless we are specifically asked to use a change of variables, then we should make sure to do so. So our first step is thinking of this change of variables, x equals 2u plus v, and y equals u plus 2v. What is the corresponding region of integration in the UV plane? And similar to a previous example, our only approach here is to break it down into individual sides. So in this case, the first side is a line going through the origin with slope 1/2. And to place this in terms of u's and v's, we simply rewrite in terms of our above substitutions. That is to say, each y is going to be replaced with the u plus 2v, and each x is going to be replaced with 2u plus v, and then we simplify. So u plus 2v is 1/2 the quantity 2u plus v. So u plus 2v is u plus 1/2 v. And in this case, we can subtract u from both sides, and then we can also subtract a 1/2 v from both sides. So 3/2 v is equal to 0. And the only way 3/2 v can be 0 is if v itself is equal to 0. So side 1 in the UV plane is going to become the line segment determined by v equals 0. And now we keep playing this game. We have side 2 and side 3. Note, side 2 is made up of a line segment that has slope -1, and if you trace it back 1, you can see that it has y-intercept of 3. That is to say, it's the line y equals 3 minus x. So each y is a u plus 2v, each x is a 2u plus v. And I'm going to let you work through the details, but note, almost identical to the work that we did to the left, you now end up with, in this case, u plus v equals 1. In terms of u plus v equals 1, that is a line in the UV plane having u and v intercepts of 1. So side 2. And then our third side is made up of a portion of a line segment going through the origin with slope 2. So y is u plus 2v, x is 2u plus v, and very quickly this simplifies down to u equals 0, which is a vertical line segment in the UV plane. And we have our corresponding region of integration, S. And we have one of the two key ingredients that we need. In order to set up our new, hopefully easier to evaluate double integral, we need our region of integration S. We need to rewrite each variable. X becomes 2u plus v, and y becomes u plus 2v. So in terms of u and v, but what we also need in here, recall, is the absolute value of a Jacobian. And I do want to note that a very common mistake is to have everything correct up to not including the Jacobian. So make sure that you're always double checking two things. Have I included the Jacobian? Have I taken the absolute value of the Jacobian? So that gives us a computation that we can do. So working that out above, the partial xy with respect to uv, we have a 2 by 2 determinant. And remember how the partials work. Across the top row, we take the partial of x with respect to u and v respectively. So 2 and 1. Across the bottom row, we take the partials of y with respect to u and then v respectively. That would be 1 and 2. So we multiply down the main diagonal to get 4, and then we subtract away what we get when we multiply down the cross diagonal. And the value of our Jacobian is 3, which is the value we substitute in to our double integral. And we now have the key ingredients that we need. What remains is to, 1, set up our limits of integration for this integral, and then 2, we need to evaluate. So let's create a bit of space. The first thing I'm going to do is just simplify the integrand. So note if that minus 3 distributes through, you'd have 2u minus 3u, so minus u, along with a v minus 6v, so minus 5v. There's a minus in each of those terms. I'm going to pull it out front just for convenience. And then there's our Jacobian, the 3. Note our region of integration, in this case S, is not simply a rectangular region that we can easily handle. It's one where we have to think a bit more about setting it up. So note side 2 became the line segment u plus v equals 1. And we can order our integration however we prefer in terms of the setup. And I don't see necessarily a benefit of doing it one way over the other. So I'm going to go ahead with dv du, simply because it's nice to observe that you have u varying between numbers 0 and 1 in our region, which would give us the outside limits of integration. Then we need to think, if you pick a value of u between 0 and 1, how do those corresponding v values vary? And they will vary from the lower curve, v equals 0, to the upper curve, v equals 1 minus u. So going back to our old techniques. And now we have a very reasonable double integral to evaluate, and we can just do so incrementally, step by step. We start with the inside integral with respect to v, and once that has been evaluated, we take care of that outside integral with respect to u. And let's go through 2 or so steps together, and then I'll leave the rest of the details up to you. So evaluating the antiderivative on the inside with respect to v, we would have uv plus 5/2 v squared from v equals 0 to 1 minus u. So we substitute in a 1 minus u, minus sign, substitute in 0. Of course, when you substitute in 0, you get back 0. So we would have u times 1 minus u plus 5/2 times 1 minus u squared. And I'll write the minus 0 just for fun, du. And what remains is now a very reasonable Calc 1 problem to evaluate this integral. And what I would suggest is that the maybe simplest way to go about this is just to do the algebra. That is, expand everything out into powers of u and then evaluate the integral. And when you do that, and I definitely think it's good practice, what you will end up with for the value of this integral is simply minus 3. In terms of the full details illustrating how this works, you can see the completed note sheet on Canvas. So this completes our discussion of changes of variables for double integrals. But as usual, there are plenty of suggested problems that would be beneficial for you to work through. And as you encounter questions, do not hesitate to drop me an email or stop by virtual office hours. So stay tuned and take care.